Hello again. In this short video I'm going to give you a quick introduction to shear. What is it and how is it resisted? Let's imagine this pack of cards. We're going to hold it at the bottom and then we're going to push it at the top. You can see that the cards have slid relative to each other, and it is this sliding or slicing action that is known as shear. So how does this apply to structural engineering? Let's imagine this steel beam. The beam is simply supported and it's spanning between two supports. Now if we apply a point load to that beam, that point load is resisted by taking those loads back to the supports. So if we break that beam up into two imaginary sections, the effect of that load is that it wants to make the two slide relative to each other. The part to the right wants to move down relative to the part to the left, and this is known as shear. So an internal shear force is applied on the one side of that line, and it is resisted by an equal and opposite force on the other side of the line. So why don't beams just fail in shear? Why doesn't the one side just slide relative to the other? Well, let's start by looking at a concrete structure. Apologies for the rough sketch, but this is a short concrete beam, and in it I'm drawing the aggregate, and you'll see how it all interlocks with each other, and then surrounding the aggregate is all the sand and cement. So that vertical red line that you saw before won't actually be vertical, because actually it's got to follow the line of the aggregate, and it's that aggregate interlock that gives us a good shear capacity, further enhanced by the cementitious bond. Unfortunately, on big heavy structures where you've got big loads, there's only so much that the concrete will do. It's not got an amazing shear capacity, but what has is steel reinforcement. So by placing some steel reinforcement in the tension zone, you can dramatically increase the capacity. Now let's also add some reinforcement in the compression zone. And we'll now tie that reinforcement in the top and the bottom of the slab with vertical reinforcement that's known as links or stirrups, depending on how it's detailed. We'll come into how those stirrups actually provide additional shear capacity in a separate video. Steel beams behave very differently, and they can carry some huge loads. The atoms are held together by a metallic bond, and it's this metallic bond which glues the whole lattice together. For an I-shaped beam taking vertical loads, the bulk of the shear is taken in the web. That is the tall, slender plate that's going vertically from the top flange to the bottom flange. Now, if we want to increase the capacity of that beam, we could thicken the web or we could deepen the web. If we make the web too tall, then it's at risk of being too slender. So what you can do, as well as thickening and increasing the height of the web, we can also strengthen it by adding stiffeners to the web. Ones in the image here are shown as transverse web stiffeners. On major structures with really tall webs, then you also can add some longitudinal web stiffeners. These can quite noticeably increase the shear capacity of the beam. So the key point here is that it's not purely about the strength of the material, it's also about the detailing. Okay, in this video I'm not going to tell you how to calculate the applied shear force or how to determine the shear capacity of a beam. They're both large topics and we'll cover in separate sessions. Obviously, the applied shear at any point needs to be less than the shear capacity. So, first of all, let's look at what helps determine the applied shear at a particular point. This could include the span of the beam, also the load applied to the beam, not just its intensity but where it's applied, and also the articulation of the beam, how it's restrained at each end. So what helps determine the shear capacity? There's material type, material strength, there's the beam sectional properties such as the height and the thickness of the web. There's also the beam detailing, which could be the introduction of stiffeners on a steel beam, like we showed in the previous example, or the way that the reinforcement is detailed within a concrete beam. Okay, so let's have a really quick recap. First of all, shear is the sliding or slicing action. The applied shear force depends on the applied load and the structural arrangement. The shear capacity depends on the properties of the member, and capacity can be improved through good design. I'm That Structures Man. I really hope you enjoyed this video. If you do, please remember to click like and subscribe. Thank you.